In this video, I'm going to talk about the invariants of a graph that we can get from these matrices that we're computing from the graph, like the Laplacian matrix or the adjacency matrix. And at first, it's going to look like they're not very good. And then with a little bit more thought, we can uncover some more interesting kinds of invariants. Now, part of what we'll do here is just say, hey, if I have a matrix that I computed from a graph, and I have this whole list of things that I know how to do on matrices from linear algebra, we can ask like which of these operations say maybe things about the graph that are invariant to isomorphism of the graph. So here's our topic: matrix invariants of graphs. And the first motivating question would be to ask, like, if I have a matrix AG, which is the adjacency matrix of a graph G, or I have the Laplacian of the graph G, is that itself a graph invariant? And the answer is yes, but no. But yes. I'll do them in this order. It's no, well, yes, and yes, but really no. And this is not the most standard way to get excited about a topic. In fact, usually it goes yes, no, yes, where you start out with something that you say like, oh yeah, that's good, and then you're like, wait, no, it's not so good, and then you figure out in what sense it's still good. But we're going to go the other way. We're going to say, oh, it's clearly not a good thing, and then we'll figure out in what sense these really are invariants, and then we'll see that they're not so useful. But don't lose hope, because what we'll find then is that even though the matrix as itself is not a good graph invariant, let's say we'll call it not a useful graph invariant, we can extract information from it. In fact, we can extract invariants from the matrix, and that's going to be our main activity. But first, let's just ask the first one, like, is the matrix itself an invariant? And of course, the reason that we start with no is that if you just look at any matrix, let's just take a Laplacian of a graph. If I were to reorder the vertices, I would get something like some permutation times that Laplacian times the permutation transpose. And so these are both Laplacians for G, just defined with different vertex orders. If I don't get the same Laplacian even with the same graph, then I'm not an invariant. But on the other hand, we saw something like this in other situations where we had different objects, but we just had to change what our idea of equality was. So we could do this. For instance, we can take matrix similarity as an equivalence relation on matrices. This means that, well, M1 is going to be similar to M2 if and only if there's some invertible matrix R where M2 is just equal to R inverse M1 R. Now, you may have seen a lot of these matrix constructions where you had a matrix and then you multiply on the right by some matrix and then you multiply on the left by the inverse of that matrix. Sometimes it's the transpose for orthogonal matrices. And if these seem strange to you, here is one way to think of them, is that these are linear transformations. Multiplying 3 of them is composing 3 transformations. And the way these particular ones work is that I apply R, which means I go to some other space, and then I do some other operation in that space, and then I come back with R inverse. And so I've written my transformation in the space where I started with in terms of going some other space, doing the transformation there, and then coming back. And so that's why you see this again and again. You'll recognize this perhaps things like singular value decomposition or other really classic constructions. All right, so if we do this, one thing we know is that for matrices like the Laplacian and the adjacency matrix, Well, they are going to be similar to another Laplacian or adjacency matrix where it just came from a different ordering, because this matrix P transpose is the inverse of P, right? That's one fact about these permutation matrices. So in this case, even though these are different matrices, they are still similar matrices. So if I say, okay, I'll take it as an invariant up to matrix similarity, then yes, the matrix itself is an invariant. But now I say no again, and the reason I'm going to like crush the optimism is that if you wanted to use a matrix as a graph invariant, and you needed to check whether or not two matrices are similar, and you know that there's going to be similar up to this permutation, that permutation actually is the isomorphism. So usually we would like the invariant to give us some quick or easier way to quickly separate out and determine that two matrices are different, that is, they're not isomorphic. But if I have to search for a permutation matrix, then I'm actually just searching for the isomorphism. I haven't made my life any easier. So in that sense, it's not terribly useful. But, okay, not all hope is lost. And that must be true because I wrote it here. And the first thing you might try is the following. What if we compute the trace of the matrix? So if you don't remember, the trace is just the sum of all the diagonal elements. And the trace has some nice properties, but one thing that should be immediately clear is that if you do this symmetric permutation, that is, I take P LG times P transpose, this is just going to rearrange the diagonal, right? So in the case of the Laplacian, this is just the sum of the degrees. And the sum of the degrees is just twice the number of edges. So this doesn't give me an invariant that's different than, say, just the number of edges. And so I would call this one kind of boring. Thinking, though, about the trace, we may get back to it. Other matrices we might have more interesting traces. We'll see. Another thing you can try is taking the determinant of a matrix. So the determinant of a matrix is going to look like well, if I take the determinant of this permuted matrix, the determinant has this nice property that if you take the product of the determinants, it's the determinant of the products. So I can rewrite this as the determinant of LG times the determinant of P transpose, right, where the determinant of these permutation matrices is both 1 or both -1. And so this is P L P transpose. And there it means that I really do have an invariant. So this permuted Laplacian, if I took a different vertex order, I'm going to get the same determinant. And that would be great. It would be so good, except there's a little bit of a problem. If you remember, the Laplacian is singular, so the determinant is always 0 anyway. So both these examples look really maybe pessimistic, but actually both of these examples are cases where you can actually get something interesting with a little bit of a modification to the matrix we look at. We won't do that now. Instead, I'm just going to point out that there is something else you may have learned, hopefully you learned when studying linear algebra, is that if you have a matrix, you can start computing things called eigenvectors or eigenvalues. So for a matrix M, an eigenvector V is a vector such that M times V is just some scaling of V. So it's just the particular vectors for which the operation of m just looks like I scale the vector. And good news is that for symmetric matrices, symmetric real matrices, the eigenvalues will be real. So we won't have to worry about getting complex numbers, which you might get if you had a matrix that was not symmetric. And so the number of these we get is equal to the dimension. So actually I could write this as vi lambda I times vi, and we get n of these for an n by n matrix. And so you could sort this collection of numbers. Now, we had previously looked at the invariant, which I think we called the score, which is the sequence of degrees of all the vertices. So this is a different sequence of numbers, and we sort it, and this will also be a graph invariant. We'll have to check that this is really true, but this one is a completely new invariant. This one is different from the ones we've seen so far. It'll give us actually some new distinguishing power. But let's check that it's an invariant. So for, again, here's a Laplacian times some vector. I didn't have to choose a Laplacian here, but that's good enough. And so this is an eigenvalue, lambda, and v is an eigenvector. If I take a permutation p, and I take w to be the permuted vector of v. So I apply the permutation to v, and that gives me w. One thing, if we just like expand everything, we see that p times lp transpose, that is my permuted Laplacian, is going to be equal to p l p transpose times w is just pv. And now this is good news because p transpose times p is equal to the identity. P transpose is the inverse of p, and there's an associative law of multiplication in matrices. So I could do this multiplication first, cancel it right out, and I get p l v. Now I know what lv is because v is the eigenvector with eigenvalue lambda. So this is p times lambda v. And linear operators, I can move the scalar multiplication to the outside. And if you recall, this PV, well, that's just W. So that's equal to lambda W. What did I get now? It's saying that if I took this permuted matrix and times it by W, I get just lambda times W, which means W is an eigenvector. It's different from the eigenvectors that I would have gotten from just L, but the eigenvalue is the same. Right, this is exactly the critical fact that we needed to be able to say that this collection of eigenvalues is an invariant. If I had permuted the vertices of the graph, which is again like saying if I had applied some isomorphism, then I will end up with exactly the same set of eigenvalues. Okay, so this is another way to extract some other invariants from the matrix. And again, these invariants now naturally encode the invariance to isomorphism. All right, so that's the game. Here's a quick recap. So if I want to go from matrices to invariants, we could do it up to similarity. I put this in parentheses because it's not really a main approach here, but it gives us some practice in thinking about invariants. We could take the trace, and for the matrix we looked at, I guess we looked at the Laplacian. It's even less interesting for the adjacency matrix because the trace of the adjacency matrix is 0. But we're going to keep this in mind because there are some cases where we can get other matrices from the graph, and then the trace will encode, again, all permutations of the vertices in that matrix. We could also take the determinant And this one has at least one very wonderful use, although again we didn't see it yet, but we can at least know that the determinant will be invariant to those permutations as well. And finally, we got the eigenvalues. This list of eigenvalues is also called the spectrum. And this is the starting point of a whole theory called spectral graph theory, which is quite wonderful in its own right. We'll get to see only a kind of a hint of it. I haven't even decided what the next videos will be, but hopefully we'll see something about the determinant, and we'll see some more interesting facts about the eigenvalues and actually also the eigenvectors of the Laplacian matrix. So stay tuned for that.